Dear students, good evening and a warm welcome to CSAT Made Easy 2025 series, where we discuss the most exam specific questions and concepts from the point of view of your CSAT paper of 25. I am Sachin Gopanal and today's topic of discussion would be number system. And as I have told you in one of the previous classes, number system is a very important topic from the angle of your CSAT paper. The three important topics from the angle of your CSAT paper, as I have told in one of the classes before, would be passages, number system and data sufficiency. Okay, let's begin the class with the first question, and as always we will begin with basic question, learn basic concept and gradually rise up to exam level questions. Let's look at question number 1. How many consecutive zeros are there at the end of the integer obtained in the product 2 raised to 200, 2 raised to 300, 4 raised to 400 and 5 raised to 500. Okay. Now, this would be a very large number, right? I think even our computers, they would not be able to calculate this product. Okay. Then how do we calculate the zeros, number of zeros that are there at the end of this product? Okay. This is a very easy concept actually. Let's read the concept once. The concept is this: the number of consecutive zeros at the end of any number is equal to the number of pairs of 2 and 5 obtained when the number is expressed as a product of prime factors. Okay. What do I mean by this definition? It means that when a number is expressed as a product of prime numbers, however many pairs of 2 and 5 you get, that many zeros will be there at the end of that number, because 2 into 5 they make up 10, that is a pair of 2 and 5 they will contribute 1 0 to the number. However, there are no other prime factors that will contribute 0. Yes. Okay. And I have also given you an example. For example, 10 is equal to 2 into 5. Okay. 100 is equal to 2 into 2 into 5 into 5, that is 2 square into 5 square. So there are 2 pairs of 2 and 5. This is one pair and this is another pair. So you will have 2 zeros. And 1000, there are 3 2's and 3 5's, that is 2 raised to 5, 2 cube and 5 cube. So you have 3 zeros at the end of 1000. However, if the number of 2's and 5's are not the same, count whichever of the two is less in number. For example, look at 20. 20 can be expressed as 2 into 2 into 5, right? 2 square into 5 to the power of 1. How many pairs of 2 and 5 do you get? Only one pair, because there are 2 2's and only 1 5. So you need to count whichever is less, because we want pair. We do not want how many 2's are, we do not want how many number of 2's and 5's are there. We want how many pairs of 2 and 5 are there. So even though there are 2 2's, we will get only one pair of 2 and 5. So at the end of 20, there is only 1 0. Let's look at another example. 2500, it can be expressed as 5 raised to 4 and 2 square. There are 4 5's and only 2 2's. So how many pairs of 2 and 5 do you get? Only 2 pairs. So there are only 2 zeros at the end of 2500. The concept is simple. The concept is simple. This is the concept. When you express a number as a product of its prime factors, however number of pairs of 2 and 5 you get, that many zeros will be there at the end of that number. And along with this, you need to know one more concept, that is AB, two numbers, product of two numbers, AB whole raised to x can be expressed as A raised to x and B raised to x. AB whole to the power of x can be expressed as A to the power of x into B to the power of x. This is one of the properties of exponents. Just remember this one. Okay. Using all these concepts, we will answer this question. Okay. How do we answer it? Have they already been expressed in terms of prime factors? No, right? This is not a prime factor. So we shall express this one as a prime factor and then we will have the answer. Two to the power of 200 into 2 to the power of 300 into 4 to the power of 400 into 5 to the power of 500. Okay. Now these two, they are already there in the form of what? Prime. These two are already prime factors. That is no worry. However, look at 4. 4 raised to 400. You can express 4 in terms of prime numbers, right? That would be 2 into 2 raised to 400. And we learnt in the previous slide that a into b whole raised to x can be expressed as a raised to x and b raised to x. So we will express this as 2 raised to 400 into 2 raised to 400. So we will use that here, 2 raised to 400 into 2 raised to 400 into 5 raised to 500. Okay. How many number of 2's do we have? 200 plus 300, 500, 500 plus 400, 900, 900 plus 400. We have 2's, 1300 number of 2's. How many number of 5's do we have? We have 500 5's. So how many pairs do we get? We get only 500 pairs. Why? Because if the number of 2's and 5's are not the same, count which of the 2 is less in number. Which is less in number? This is less in number. So that many pairs of 2 and 5 we get, and that many zeros we will get at the end of this number. So what will our answer be? Our answer will be option A, 500. Okay. This was an easy question, easy concept. We understood the concept of number of zeros at the end of any number. Okay. Let's go to the next question. How many consecutive zeros are there at the end of the integer obtained in the product? 1 to the power of 1, 2 to the power of 2, 3 to the power of 3, 4 to the power of 4, up to 25 to the power of 25. Okay. How do we do this one? This, it looks like a very lengthy process. However, which are the numbers that they have used? They have used the numbers from 1 to 25, and to what power have they raised each number? They have raised each number to the power of itself, that is 1 to the power of 1, 2 to the power of 2, 3 to the power of 3, 4 to the power of 4, 5 to the power of 5. That way 25 to the power of 25, 24 to the power of 24, 23 to the power of 23. This is what they have done. And now the technique that we will use to solve this problem is this. We will consider only those numbers within which have a prime factor of either 2 or 5. The rest of the factors, they do not concern us at all. For example, look at 3. However many 3's be there in the number, it doesn't matter to us. However many 7's be there, it doesn't matter. However many 9's be there, it doesn't matter to us. Only those numbers which have a factor of 2 and 5, we will consider only that ones, because they are not asking us to find the value of this product. They are only asking us to find the consecutive zeros at the end of the product. So we know that only 2 and 5 contribute to zeros. 1 2 and 1 5, a pair, they will contribute to 1 0. That is the concept. Okay. Look here. How many number of 2's are there in the number 2? It is only 1. In 4 there are 2 2's. In 5 there is 1 5. In 6 there is 1 2 and 1 3. Okay. We don't bother with 3. In 8 there are 3 2's. In 10 there is 1 2 and 1 5. In 12 2 2's and a 3. In 14 1 2 and a 7. In 15 1 5 and a 3. In 16 there are 4 2's. In 18 there are 2 and 9. In 20 2 to 5. 2 into 11. 2 into 2 into 3. 5 into 5. By looking at this, we can observe one thing, right? Many numbers, they have 2's, and the numbers which have 5 as its factor, they are very less. 2 2 2 2 2 2 2 2 2 2 2 2. But 5 5 5 5 5 and 5. So even if you count all the 2's and all the 5's, the number of 5's will be less than the number of 2's. So we know that when the number of 2's is not equal to the number of 5's, we will consider the number of 5's only, because we need to consider only whichever of the 2 is less. So we will count only 5's here. Counting all the 2's, it doesn't give any benefit, because number of 2's, by looking at this chart, we know that number of 2's are more than, it is more than the number of 5's. So we will count only number of 5's, and that will give us how many pairs of 2 and 5 we get, and that will give us how many zeros are there at the end of this product. Okay, here 5 is raised to 5, so we will get 5 5s here, and 10 is raised to 10, so we will get 10 5s here. Here 15 is raised to 15, so we will get 15 5s here, and here 20 is raised to 20, so we will get 20 5s here, and here 25 is raised to 25, so we will get 25 and 25, 50 5s there. So how many 5s do we get in total? Here, 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 here and here. Okay, let's add them. It is 5, then it is 10, then here it is 15, here it is 20, however there it is 25 plus 25, 25 plus 25. Now we will add them. 5 5 5 5, that would be 20, 2 carry, 1 2 3 4 5 6 7 8 9 10 100. So in this product there are 100 5s. So you may count the number of 2s. As a homework you may take it, count all the number of 2s, they will be greater than the number of 5s. We have 100 5s here, so we will have 100 zeros at the end of this product. So what will our answer be? Our answer will be option C, 100. Okay. The logic behind this question is, we just need to make what the pattern is. It is 1 raised to 1, 2 raised to 2, 3 raised to 3, 4 raised to 4, and we need to identify how many number of 2s and 5s are there in those this product, and we need to see whichever is less and we'll count that one, and that will give us the number of zeros at the end of the number. Okay, let's go to the next question. How many consecutives are there at the end of the integer obtained in the expression 1 square divided by 1 square into 2 to the power of 4 divided by 2 cube into 3 to the power of 6 divided by 3 to the power of 4, 4 to the power of 8 divided by 4 to the power of 5, and ultimately 25 to the power of 50 divided by 25 to the power of 26. How do we solve this one? This looks slightly tricky, however it is not. I will tell you why. This question, it is based on this concept. A to the power of x divided by a to the power of y, it can be expressed in the form of a to the power of x minus y. For example, if you had 10 to the power of 10 divided by 10 to the power of 9, we could express it as 10 to the power of 10 minus 9, that would be 10 to the power of 1. Okay, this is just an example, and we will use that concept to solve this question. How? Let's take these two, 1 to the power of 2 divided by 1 to the power of 2. Okay, but are they in any pattern? Because we cannot go on doing each for each of the numbers, right? Okay, let's see if they are in pattern, and we will simplify that pattern. It is 1 raised to 2 divided by 1 raised to 2. Okay, they are the same number, so we cannot make out any pattern. This is 2 raised to 4, this is 2 cube. Okay, this is 3 raised to 6, this is 3 power 4, this is 4 raised to 8, and this is 4 raised to 5. I think we can make out a pattern. Look here, it is 1 to the power of 2 into 2 to the power of 4 into 3 to the power of 6 into 4 to the power of 8 and into 25 to the power of 50. So whenever there is an into, each number is being raised to the double of itself. 1 raised to double of 1, 2 raised to double of 2, 3 raised to double of 3, 4 raised to double of 4, and 25 raised to double of 25. Then when there is 20 divided by, each number is being raised to 1 more than itself. 1 to the power of 1 plus 1, 2 to the power of 2 plus 1, 3 to the power of 3 plus 1, 4 to the power of 4 plus 1, and 25 to the power of 25 plus 1. Okay, so we made out the pattern here. Now we shall use this one and apply this concept to get a simplified form, so that we can calculate the pairs of 2s and 5s that are there in this expression. So the first expression, 1 to the power of 2 divided by 2, it would be 1 to the power of 2 minus 2, because a power x divided by a power y, that would be a power x minus y. Okay. Then 2 to the power of 4 divided by 2 cube, that would be 2 to the power of 4 minus 3. Okay. Then 3 to the power of 6 divided by 3 to the power of 4, that would be 3 to the power of 6 minus 4. And 4 to the power of 8 divided by 4 to the power of 5, that would be 4 to the power of 8 minus 5. And ultimately 25 to the power of 50 minus 26. Okay. What will this expression be? It would be 1 to the power of 0 into 2 to the power of 1 into 3 to the power of 2 into 4 to the power of 3 into, and that way up to 25 to the power of 24. Okay. What is happening here? Each number, it is being raised to 1 less than itself. 1 to the power of 1 minus 1, 2 to the power of 2 minus 1, 3 to the power of 3 minus 1, and 4 to the power of 4 minus 1, and ultimately 25 to the power of 25 minus 1. Okay. And remember one thing, 1 to the power of 0, it is 1. It is not 0. 1 to the power of 0 is 1. Okay. Now we know however many 2's and 5's we can extract from that expression. Okay. And we know that the number of 2's, they will be more than the number of 5's. So we'll count only 5's. Okay. What will this 5 be raised to? It would be 5 to the power of 4, right? Okay. What will this 10 be raised to? It would be 10 to the power of 9. Okay. This 5 would be raised to 9. Here it would be 15 to the power of 4. So here 5 would be raised to 14. 15 to the power of 14. So 5 would be raised to 14. 20 to the power of 19. So here 5 would be raised to 19. Here 25 would be raised to the power of 24. So we would have 2 sets of 24 5's. So okay, we shall count the number of 5's here. Here, and ultimately here. Okay. Here we have 4. Here we have 9. There 14, 19, and ultimately 24 and 24. Okay, let's add them. 4 and 9, 13, 17, 26, and 34. We will take 3 carry, 5 and 9. So we have 94 5 as factors in this expression. In this expression we have 94 5's, and if you count all the 2's, they will be more than the number of 5's. So we will count whichever is less. So our answer will be 94, because we can make out only 94 pairs of 2 and so 5. So what will our answer be? Our answer will be option C, 94. Okay. Only the simplification of this one was a bit tricky here. The rest of it you already knew the concept. I hope that you understood the concept. Now it's time to go for your homework question. This is your homework question. It was asked in the 24 CSAT paper. How many consecutive zeros are there at the end of the integer? 1 square, 2 raised to 4, 3 raised to 6, 4 raised to 8, and 25 raised to 50. So each number is being raised to the double of itself. Okay. Use this concept and count the number of 5's, and that will give you the answer. You need not count the number of 2's. However, if you want to make sure that the number of 2's are more than 5's, just go ahead and it will be more than 5's. Okay. So answer this question and leave your answer in the comment section. We will discuss the answer to this question in the next class. Okay. And now it is time to answer the homework question of the previous class. This was your previous classes homework question, right? What is the rightmost digit preceding zeros in the value of 30 to the power of 30? And how do we answer this one? It is based on the concept of cyclicity of unit digit, right? 3 raised to 1 is 3, 3 square is 9, 3 cube is 27, 3 raised to 4 is 81. So look at the last digit 3971. It forms a cycle. See here, 3 raised to 5, 3 raised to 6, 3 raised to 7, 3 raised to 8. The unit digit are again 3, 9, 7 and 1. They are forming a cycle. And here 3 raised to 9, 3 raised to 10, 11 and 20. Again the same unit digit 3971. So the last digit of any, when you multiply 3 with itself or when you multiply any number with itself, that number if it is ending with 3, the last digit of the product, it will be cycling 3971, 3971, 397 and the cycle length is 4. We will use this concept to answer this question. How? What is the number given here? It is 30 to the power of 30. And how do we express 30 to the power of 30? We can express it as 3 into 10 to the power of 30. Yes. And we learned that whenever we have AB to the power of x, we can write it as A to the power of x and B to the power of x. So this would be 3 to the power of 30 into 10 to the power of 30. Okay. And this expression 10 to the power of 30, it will only contribute to zeros. So we will ignore this one because the question asks us what is the rightmost digit preceding zeros in the value of 30 to the power of 30. And this is the term which will give us those zeros. So we will ignore this one. And whatever will be the last digit of this term, it will be the digit preceding the zeros, right? What is 3 being raised to? 3 is being raised to 30, and we know that when 3 is raised to 3 is raised to one number and raised again and again and again, for every 4 times it is being raised, it is being multiplied with itself. The cycle repeats 3971, 3971 and 3971. 3 to the power of 4 is 81. 3 to the power of 4, it will have a last digit of 1. 3 to the power of 8, it will have a last digit of 1. 3 to the power of 12, it will have a last digit 1. Similarly, 3 to the power of 16, it will have a last digit of 1. 3 to the power of 20, it will have a last digit of 1 because the difference is 4. 4, 8, 12, 16, 20, 3 to the power of 24, 1. 3 to the power of 28, that would also be 1. However, we want 3 to the power of 30, right? After 1, the cycle will repeat, right? We will get 3 to the power of 29, we will get 3, and 3 to the power of 30, we will get 397139. So for 3 to the power of 30, we will get some number which will be ending with 9 multiplied by 10 to the power of 30. This 30 to the power of 30, it would be some number ending with 9 into 10 to the power of 30, and this will contribute to the zeros. So what is the rightmost digit preceding the zeros at the end? That would be 9. So what is your answer? Your answer would be option D, 9. Okay. I hope that you found today's class beneficial and helpful to you. If you liked the class, do watch us regularly. We upload one episode every evening, and do share the YouTube link to this video with your friends on WhatsApp groups and Telegram groups. And I wish you all the best, and most of all, I wish you a very happy studying. Thank you.